In this lecture, we look at stationary fluids. These are sometimes also known as hydrostatic problems. Imagine a block of water in a pond at some depth. The block has a height of d. The block doesn't move, so the net force on it must be 0. The block of water has a weight, so it has a force downward of minus mg. And then there's also a force downward due to the mass of water above it, or the pressure pushing down on the block. That's F down. And then there's the force due to the water underneath the block. The pressure from that water pushes upward. And that gives you F up, and since it's not moving, the sum has to be equal to 0. We rearrange that, and the force up is equal to the force down plus mg. And we write that in terms of pressure. The force up is equal to the pressure on the bottom of the block times the area of the bottom of the block, which is equal to the force down, which is the pressure on top of the block times the area of the block, plus the mass times g, rewritten in terms of the density of the water, times the area times the height of the block d, times the acceleration of gravity. If we cancel out the areas, we have that the pressure at the bottom is equal to the pressure at the top plus rho times d times g. If we're interested in the pressure below the surface or in relative to the surface, we can just put our block so the top is at the surface and rewrite our equation so that it's P as a function of d is equal to the pressure of atmosphere, that's pressure at the top, plus rho times dg. So let's take an example. Pressure 3 meters below the surface is equal to the pressure at 3 meters, which is 1 times 10 to the 5th pascals, the pressure at the surface, times 1,000 kilograms per meter cubed, the density of water, times 3 meters times 9.8 meters per second squared. And this is equal to 1.3 times 10 to the 5th pascals. So for every meter, you get a tenth of 100,000 pascals, or a tenth of an atmosphere. Let's take a look at an example of a water tower. The top of the water in a water tower stands 30 meters above the ground. What is the water pressure at the pipe at the base of the tower? We'll take that to be at the ground level. Although the shape of the container is different, this is the same problem as the pond. Replace the depth d with the height h in our equation, so we have P of h is equal to the atmospheric pressure, which is what's at the top of the water, plus the density times h times g. So that P at 30 meters is equal to 1 times 10 to the 5th pascals times the density times 30 times 9.8 meters per second squared, or in other words, 4 times 10 to the 5th pascals. Again, remember this is absolute pressure. If we're interested in the relative pressure with respect to the atmosphere, or what's sometimes known as the gauge pressure, this is also 45 psi. And this is a typical water pressure for a city's water supply.